Great. So the Wronskian is e to the 8x. Awesome. So now we can find the u1 and the u2 as long as we know the formulas. So u1 is negative the integral of y2 times f, all divided by the Wronskian. So let's see if we can plug everything in here. So that's negative the integral of, so y2 was what?
E to the 4x
right, e to the 4x sine x, great. And then the capital F, can you remind me what that comes from again?
The right side of it.
Yeah, that's just the right side of the whole back, the whole original problem. Back at the start, so we had e to the 4x cosecant of x right there. Okay, so that's the f, and then I divide by the Wronskian, which is e to the 8x. So this is what we have to do. Anybody know how to simplify that?
The e's cancel out.
All the e's cancel, and what about sine and cosecant?
They cancel too.
They also cancel. Oh man, this is so easy. Okay. So this is just a minus x.
Yeah.
Do I need to put plus c on that?
No.
You can, but you don't need to. Because you can just choose c to be 0. So I would just do that. So that's u1, it's like that. All right, and then u2 is going to be positive the integral of y1 times f over the Wronskian. Maybe this one will be slightly harder. Let's see. So this is the integral of the y1 was e to the 4x cosine of x. Capital F is the same, e to the 4x cosecant of x. I'm dividing by the Wronskian, which was
E to the 8x.
e to the 8x. Okay, so this time the exponentials actually cancel again. And cosecant, okay, I don't quite know how to combine those, but I do know that cosecant is just 1 over sine. So I can write that actually as cotangent of x. Okay, cotangent of x, and this one is in your integral table. So do you have it for me?
Natural log of sine x.
Okay, so that's natural log of
Absolute value.
absolute value of sine of x, yeah. Okay, great. So that's my u2 formula. Everybody good with that?
Yeah.
Okay, so we did the Wronskian, we found the u1 and the u2, not too hard. Again, if you come up with an integral that looks monstrously bad, and it's not in your table or even close to something that's in your table, probably there's something wrong. So I would suggest that you don't just erase it right away, but rather think about going on and coming back. Because it could be that what's wrong was just you made a minor mistake. It's not worth it could be that all the work you try to do to fix that one little mistake is worth 2 points or something because your mistake was so minor you just didn't it looks like you have a disastrous answer, but you actually were very close to the right answer. You'll get most of those points. I would suggest you move on. And then, yes, if you have time later, go back and try and fix those points. But you need to be, my point about taking tests here, guys, is you need to be going for the big points first. Okay, if you're fixing if you're confident that you did the procedure right, you know the process, and somehow you're getting an integral that's not reasonable, it probably means you made a mistake on something that's not worth a lot of points. So don't fuss over that part yet. Save it until the end. Okay, so, great. So now we can go to the particular solution. So you remember the formula?
Yeah, u1, y1.
u1, which is negative x, times
y1.
y1, which is e to the 4x cosine of x. Okay?
Plus u2.
Plus u2, which is ln of absolute sine of x. Times
y2.
y2. Very good.
We don't need A and B before that?
No, the a and the b, that comes in the annihilator method. That's the other type of problem. So we haven't done one of those yet. So this is just the particular solution. And so then finally, y of x is equal to, this is step 3 in my 3-step process. You just simply add together the complementary function and the particular function. And I'm okay with you just writing this down as long as you have identified why. If you make me guess, so I see people sometimes do stuff like that. They'll just have that up on their paper. And, or they won't have this here. And then it'll be there, and then they'll say, oh, it's yc plus yp, but you haven't told me what's what. You're going to lose points for that. It has to be well labeled. So this would be y sub c of x, and this would be y sub p of x. So I'm okay with you doing the shortcut, but just make sure it's clear. Okay? All right, so that's just an example of the variation of parameters. All right, well, there's lots more lots more things we can go over here. I'm gonna do something a little more on the theoretical side. I think we want to talk about the kernel and the range a little bit, and go back to the earlier stuff, and you know, we'll get back to the annihilators and all that good stuff in a little while, but I just want to try to cover a variety of things. So I'm going to go ahead and jump up to number 11 and do a quick theoretical problem. Okay, here's what it says. If t from v to w is 1 to 1, and v1, v2, v3 is Li. So if I take three vectors that are Li, and I have a one-to-one function, show that the set T of v1, T of v2, T of v3 is Li. So we actually did this one in class, I think, or it might have been a homework problem. I can't remember whether it was just an example or a homework problem. But we have actually looked at this before. I just want to do it again because it's going to review Li, it's going to review one-to-one. Remind me again, what does a one-to-one transformation mean?
The only thing that is killed by the transformation is the trivial solution.
Okay, the only thing that's killed by the transformation is the trivial solution. What is that set called again? The kernel. So the kernel is trivial. Right, so we are assuming that the kernel is trivial. You know, here's another test tip. Let's say you don't know have any idea how to do the problem. But if you would just write down what you do know, you're going to get some partial points. So for example, the kernel of T, right, you could say is 0. This is what one-to-one means. Okay? I'm not expecting you guys to like produce something that like would go in a math journal. It just has to be like, you know, give me the highlights here and make it comprehensible, and I'll be okay with it. Does anybody remember what Li means? Want to try it? Say it one more time. Okay, so C1 times V1 plus C2 times V2 plus C3 times V3 equals 0. An Li set is one where the only way that that can happen is if you have to cheat and make all of the constants 0. In other words, you can make them cancel out in the easy way, which is to just put zeros in front of everything.
Mm-hmm.
So you need to show that, basically. But actually, you're trying to show it about this set. So instead of starting with V1, V2, and V3, I'm actually going to start with T of V1, T of V2, and T of V3. So I'm going to assume that C1 times T of V1 plus C2 times T of V2 plus C3 times T of V3 is equal to 0. I'm going to start with that. Linear independence is kind of a tricky one because it's like an if-then condition. If we have this linear combination canceling out, then the constants are 0. So I'm going to try and show that all of the constants are 0. Okay. Now, when you see that equation like that, do you have a knee-jerk reaction? It's like, boom, I know exactly what is staring at me that I would want to do, without even thinking. Yeah?
Well, T respects addition and multiplication, they can subtract them.
T respects addition and scalar multiplication, exactly. So I'm going to put everything inside the parentheses. I'm going to put the constants in, the plus signs in, and I'm just going to write it as T of C1, V1 plus C2, V2 plus C3, V3. Maybe you're totally missing out on the linear independence part of it. You don't quite get that part. But again, if you write this step down, that step is worth some of the points, right? So I would be okay with giving you partial credit for that one single step there. So that's good to have. Okay, so I have T of this vector, whatever it is, gets killed. So what are you going to do?
Well, the inside is already Li. We know that, so that because of it says it in the problem.
Mm-hmm.
So the only way that C1V1 plus C2V2 plus C2V3 equals 0.
Okay, hold on now. Why does C1V1 plus C2V2 plus C3V3 equal 0?
Because
C1
they're LI.
Because
No.
C1 is equal to C2 is equal to C3, which is equal to 0.
No.
No.
No. Why is, the next step is, this is the next step. C1V1 plus C2V2 plus C3V3 is 0. Guys, linear independence does not tell us that. Linear independence tells us that if this is true, then the constants are 0. But I want to know, why is this true first? Give it another try.
Yeah. So is it because the functions it's 1-to-1? So
Yes.
then it has to be 0.
The kernel is trivial. The only thing that t can kill is the 0 vector. But look, here's something that t is killing. But the only thing that that could be, if we believe the 1-to-1 condition here at the start, the only thing that could be killed by t would be the 0 vector. So this expression in parentheses must be the 0 vector. That's why. So this is since t is 1-to-1. Everybody okay with that? That's a key step. Now I have this linear combination. The t is now gone. And I have a linear combination of my original vectors that cancels out. So what am I going to be able to do now?
C1 equals C2 equals C3 equals 0 because they're LI.
Right. Now we use the Li. That comes at the very end, right? At the very end, the scalars are 0 because the only way that the V1, V2, and V3 can cancel out is if we cheat. We have to make all the constants 0. So this is a very short proof. I like this proof because it reminds me what 1-to-1 means. It reviews the format for checking linear independence, kind of in an abstract context. That's the way the write-up would go. I don't expect it to be perfect, but I need to see some of these steps. The more of these steps I see and the more they are in the right order, obviously the more partial credit you're going to get. What so many students do on these kinds of problems is they just completely punt altogether. It's like, don't do anything on it, and then I can't help you. So try and do what you can, even if you don't see the whole solution. Sometimes you won't see the whole solution in your mind before you start. You just have to think about, well, what are the pieces that I know, what are the definitions that I know, and what are some of the steps that I think are going to be involved here. You can really get more partial credit than you realize. Each individual step is not that big of a leap. Okay, so just wanted to practice one of those. Maybe let's do, question? Okay, let's do one more theoretical example. As long as we're thinking on theoretical examples, then I'm going to come back to the kernel and the range again. But I'm going to do one more theoretical one that is related to the linear algebra here. So let me do number 2 on the review sheet now, since we're kind of in theoretical mode. Okay, so here we go. Suppose we have A as a square matrix. And let's suppose it has eigenvalues lambda 1 not equal to lambda 2. So lambda 1 is different from lambda 2. Okay, and let's suppose that, I'm just going to abbreviate here, guys, because you have the handouts and you can always look up the details of it. There are corresponding eigenvectors v1 and v2. Okay, show that v1 and v2 is Li. So, I mean, basically the point is, if you have eigenvectors that go with different lambdas, they are Li. Okay, there's no problem with that. So this is what we were checking. We use this all the time without even realizing it when we're solving a lot of those problems. Okay, so again, remind me, if I want to show that these are Li, what am I going to start off with? And if you need to cheat, you can look at an example over here. But how's it going to start off? Assume what?
C1 V1 plus C2 V2 equals
Great. Assume that C1 V1 plus C2 V2 is 0. Suppose that we can get them to cancel out in a linear combination. And then what is it that we would be wanting to show right about now?
That it only works when C1 equals C2 equals 0.
Right, that we want to show that both constants are 0. We want to show that both constants are 0. Okay. Okay with that part?
Mhm.
Okay, any suggestions here what we could do?
Should write down that relationship with the A and
Okay, let's say we don't know what to do, but we are thinking about partial credit. Right? Don't know how to do it, but I want partial credit. I'm going to come back up here and say, wait a minute, I know that I have an eigenvector equation for this information, and Dr. Annan's going to give me partial credit just for writing that down. So that's exactly what you would want to do next. So can somebody tell me what the equation would be? Because of the quiz, a lot of people didn't write it down very carefully. AV, I don't see a V up there. AV1, okay,
It's equal to
equals
lambda
lambda
1
1
v1.
V1. Great. Okay, just make sure we have all the notation. So we have that, and then what else do we know? AV2 equals lambda 2 V2. Okay, perfect. So those are the equations. I would want to get that down on paper to get myself started. Okay, now there's some partial credit right there. Now how am I going to use that? So I got these things in boxes right now. Anything I can do, now we need a little bit of a creative step to get us over the hump here. Does anybody see what we would do to kind of, this is really where we're starting from, and we have these equations to help us. Is there something we could do here? This equation in this box, does it have the matrix A in it anywhere? Well, as long as it doesn't have the matrix A in it, I can't really take advantage of this. Is there a way to put the matrix A into this first equation? Yeah, how about we just multiply both sides of the equation by A? So in other words, A C1 V1 plus A C2 V2 equals A times 0. What is A times 0 going to equal?
0.
0, right? That's just still 0. Okay, great. Let's just see where we get with that. Okay, so I put the A in there now. Now, does that help me at all? What can I do? Pull the constants out in front. I like that. So we'll put C1 in front, and then it's AV1, and then plus C2 AV2. That adds up to 0. Okay, and now what can I do? I don't even know quite yet how I'm going to get my final conclusion, but I'm making progress on getting partial credit with each and everything I do here.
Yeah,
Substitute
from that equation.
these equations, right? Now, because I have AV1 and I have AV2, let's do that. So we'll have C1 lambda 1 V1 plus C2 lambda 2 V2 equals 0. Okay? I'm going to erase what we're trying to show now just to make myself have a little bit more room here. I'm going to go up just a little higher. Sorry, Luis.
No, you're good.
Okay, so we have this equation down here.
Yeah.
And of course we have the equation that we started with. And we've multiplied through by A, and we've used this information here. Anybody have a suggestion what we could do next?
Well, would you be? I'm not sure the steps, but wouldn't you would use that lambda 1 doesn't equal lambda 2? So
We're
then
going to need to use that still. We haven't quite put that into the problem yet. But let's let that come to us here. We have two unknowns, right?
Yeah.
Which are C1 and C2. We would like them to be 0. We just don't know yet. And how many equations do we have involving those two unknowns, C1 and C2? We have two equations, right? We have two equations, which are this one and this one. This one and this one are my two equations. And I have two unknowns, which are C1 and C2. I would like to hope that maybe with 2 equations and 2 unknowns, I could solve for the unknowns.
You move just
Get 0 out of it.
both, or one of them to the other side with the 0 on the first equation.
Yeah, why don't we do that? So if we move one of them to this, let's say we say C1, V1, and we solve it to the other side, negative C2, V2. Why would you want to do that? Then I can sub C1, V1 down here, right? C1, V1? Exactly, so let's do that. C1, V1 is negative C2, V2, and then there's a lambda 1 that I don't want to forget about. Okay? And then plus C2, lambda 2, V2 equals 0. See, I've eliminated the V1 from the equation. Okay? We're getting close.
Yeah.
What can I do with this?
Factor out
In fact,
I have some common terms on both of those
Yeah.
terms. So the C2 is a common term. What else is common?
V2.
And V2, right? So C2, V2, right?
Yeah.
Now what else is left? Well, then I have a minus lambda 1 in the first entry, and then I have a plus a
Plus
lambda
lambda
2
2.
in the second entry. All of that has to come out to 0, right?
Yeah.
Now this is not a very good way to write it, but honestly I wouldn't take off points for this because I've put a number here and then a vector and then a number. Numbers are usually pretty safe, like you could put them before or after the vector, but technically I should probably have this constant over on the left side, but I'm okay with it being here, okay? Now this whole thing comes out to 0, right?
Yeah.
Now, can this be 0?
No,
Because they're
because
not
they don't
equal.
equal.
No, because we said they're not the same, right? So that one is not 0, for sure. I'll cancel it. Can the V2 be 0?
No,
No.
because that's one of the.
It's an eigenvector, right? Eigenvectors cannot be 0. So that's also not 0. So what are we going to have to conclude now?
C2 must be.
C2 has to be 0, doesn't it? C2 has to be 0. This is good. We wanted that.
Yeah.
Now, if C2 is 0, we still want to get C1 to equal 0. Is there a way we can get that?
Plug it back into the original formula. Or
Will you reverse the process?
Actually put it into either here or here, it doesn't matter. If I put it into here and
Oh.
put 0 for C2, then that term is gone. And now I have this times this equals 0. Is V1 equal to 0?
No.
No, so C1 has to be 0.
Yeah.
Probably somewhere along the line I should have written down that both of these vectors are not the 0 vector. If we have an eigenvector, remember that it can't be 0. Eigenvectors cannot be 0. Okay? A little bit of effort to come up with that, but there's a lot of partial credit steps here. These problems are not going to be worth 20 points. These problems are going to be worth like 5 points. And if you get a lot of the pieces written down, you probably get like 2 or 3 points at least just for that. So probably the tricky steps, which maybe would be what? Knowing to multiply through by A, that's a little tricky. And then knowing that I have 2 equations and 2 unknowns and need to substitute them back into each other, that's a little tricky. So you've got a couple of tricky steps that are probably worth a grand total of 2 points. Right? And if you don't see them, it's not the end of the world in terms of the test. But getting some of these basic things down is where you're going to get a lot of the partial credit. So please don't just punt on these problems. Write down what you can because you're going to get more points than you realize. Okay? All right, so that's that. Let's go ahead, as long as we're, as long as we were talking about linear transformations here, I think I'm going to come back over here and do some actual kernel and range stuff. So I've done problems 2, 3, 4, well 1, 2, 3, 4, and 5 we've done. Part of 6 and 11, so I really need to hit 7, 8, 9, and 10. And then maybe some more of problem 6. 6 has several parts. And now we may run a little bit past the hour that I said, but as long as you guys are awake and want to keep going, I will. I'm fine with that. So let's try I'm going to do number 9 first, because I think it's kind of the best one to get us going on this. So number 9 on the sheet, I have a transformation T that goes from M2 of R to P2 of R. And the formula is T of A, B, C, D. So this is given in the question here. A minus B plus D plus negative A plus B minus D times x squared. And then the question is part A, find bases and dimension, for the kernel of T and the range of T. This is like a standard problem, standard example. Okay. And then the second part of the problem is just going to be, is it one-to-one onto both or neither? We'll come back to that in a minute. Okay, do you guys want to start with the kernel, or do you want to start with the range, or does anybody care? Doesn't really matter to me. Kernel? Okay, I'll start with the kernel. Can you guys remind me again the kernel of T? What is that talking about?
The null space.
The kernel of T is the null space of a matrix when we have a matrix. We do not have a matrix here. Now let me be very clear. These matrices are not the matrices that we would find the null space of. These are the vectors themselves. The case where, this is very important, and you're going to see this in the review packet as well. When you have a transformation from Rn to Rm, which is not what we have here, but when you have that, you will always have, the formula will always be T of x equals Ax, and A will be an M by N matrix. In this context, the matrix, capital A, is not the vector. The vector is x, right? That's the input. So in this kind of a problem, the matrix is not the input or the output. The matrix is the tool that transforms the vector. Right? That's what's going on here. The matrix is the tool that transforms the vector. When we have this situation, now the kernel of T is the null space of the matrix. And while I'm at it, I'll just mention that the range of T is the column space of the matrix. So if I give you a transformation from Rn to Rm, and I ask you about the kernel and the range, it's simple. You just find null space and column space. Which really just means you take the matrix and you row reduce it and you find your pivots and go through the null space and column space process from back in chapter 4. But that's when you're going from Rn to Rm. Here we are not doing that. Yes, there are matrices in the problem, but the matrices are playing a different role here. Here the matrices are actually the inputs to the function. They're not the tool that's transforming the vectors like they are over here. So in this context, you really have to go back to the more abstract definition of kernel, which is that it's the set of vectors that get transformed to 0. Okay? It's just those vectors that get killed, basically. Those vectors that get killed. So what you're going to want to do to find your kernel is just set your transformation equal to the 0 vector. In other words, you're just going to set the right-hand side equal to 0. So to do this one, you're just going to set T of A, B, C, D equal to 0. Really, that just means that A minus B plus D plus negative A plus B minus D x squared is equal to 0. Okay? Clear so far? In looking at this equation, am I going to be plugging a number in for x in this problem at all?
No.
No, the x is not something you're evaluating. The x is like a placeholder. It's keeping track your constant term, your x term, and your x squared term is like separate terms.